Alright, so this lesson 7.2, we're talking about transforming exponential functions. Alright, transformations of exponential functions. We've talked a lot about transformations of functions in this course already. So we are going to take a look specifically at the transformations that are associated with an exponential function right here. Okay, that's what we're looking at. Let's see if this copies here. Oh, that's pretty good. Okay, so 7.2, transformations of exponential functions. And this is the pattern. That's the format. And that's actually not real good because you can't really tell that this is an exponent. So this is up in the exponent. Alright, so I guess I'll have to rewrite it anyways. So if we have a function that's exponential, here is the exponential function that we've studied, right? Just a basic exponential function. What we're going to talk about today is how a affects the exponential function. Now, what did a do before for other functions? Shout it out. A vertical stretch. Okay, vertical stretch. So we might expect a vertical stretch for this particular exponential function. What about b? B goes up here. So what did b do? Horizontal stretch, right? It either compressed it or it stretched it out horizontally. Good. And now what about h? Okay, again, this is horizontal. Yes, b is horizontal, h is horizontal. Remember, it's with the x here. Okay, x-axis is horizontal, so think sideways. Sideways stretch, sideways translation. And so the other thing is it's x minus h, so if h is positive, it moves to the right, but it'll show up in here as x minus, right, if it's positive. So if it's x minus 5, it should show up as a translation 5 units to the right. Okay, that's what we're expecting anyways. We'll confirm this in a minute. And then plus k. This k is not in the exponent position, so I'm actually going to get rid of this here now. Okay. And what did k do for other transformations? Okay, a vertical translation. Very good. Okay, very good. So stretch, stretch, and translation, translation. This is vertical. This is vertical. And these ones were horizontal. And this one was horizontal too. Okay. Not that we needed all that, but that's what we're expecting. So let's pop over to Desmos over here somewhere. Where is it? Over here. Okay. Pop over to Desmos and let's just see if that's the case. So what do I have? I have y equals 2 to the power of x. I have that lit up right now. Let's do y equals a times 2 to the power of x. Okay? And I've got a equals 1. That's the same as y equals 2 to the power of x, right? It's multiplied by 1. So if I move this slider and I go greater than 1, watch what happens to the graph. Now, is that a vertical stretch? Okay. It's kind of weird if you look at just this picture right here. It looks like it's sort of bending over, right? It looks like it's sort of like getting peeled away. So is it coming, this way, in this direction, or is it actually being vertically stretched? Well, if we zoom out a little bit, or a lot, I guess. Here. Okay. So if we go back to 1, okay, and I go up again, a little tough to tell, isn't it? But I think you guys are right that this represents a vertical stretch, although this is a little difficult to find out. So let's do this, let's do 3. Let's just do 3, okay. We'll zoom back in. Get rid of this. We'll zoom back in. And we'll focus up here a little bit. Actually, we can focus right here in this axis right here. Look at this. You see something interesting? There's 1. We know that our y-intercept for a y equals cx is always 1. So y equals 3 times cx, the intercept we would expect to be 3. Okay. Here, the y value is 2, so at this same x value, we expect it to be what? 3 times 2. We expect it to be 6. So let's just see. Go up. Look at that. It's exactly 6. So if you do this over and over, each y value on the original parent function or the original mother function should be multiplied by 3, the a value. So if we move that down to 2, right, then we have 1 to 2. Then we have 2 to 4. You see that? So it is a vertical stretch. Congratulations to you for predicting that. All right, what about b? What about the b value? Okay, so when b is 1, we have the same as y equals 2 to the power of x. So if I move b greater than 1, what should happen, do you think? What's going to happen to this graph? Greater than 1. It's a horizontal stretch, but when b is greater than 1, would you expect this graph to go further out or to become compressed in? Further out or compressed in? Okay, let's see what happens. I'm going to take b greater than 1. Oh, look at that. Now this one's easy to see. It's getting squished in towards the y-axis. See that? So each x value is being multiplied by 1 over b. Remember that? So let's just see. Let's just make this 4. All right. So each x value, here's an x value of 1. So that should be 1 over 4. And what is that? 0.249. So that's pretty much 0.25, right? I can't really get that any better. Yes, I can. See that? 0.25. So it's being compressed in by a factor of 1 over b. So that means if b is less than 1, let's bring it down less than 1, it should stretch out. Okay? Now, when b equals 0, what happens? Ooh, it's y equals 1. Why is that? Why is this a horizontal line through y equals 1 if b is 0? Because 0 as an exponent, well, yeah, there is an x. It would be 0 times x. So it would be y equals 2 to the power of 0, which is always 1, no matter what x is, right? Good. So if I go less than 0 into the negatives, there we go. So it appears to be that we have that's b equals negative 1. So where's the reflection there? Across the y-axis. Okay, does that make sense? So let's just take a look at that. Let's just play that. So 0 to 10. That's 10. Back down there. See that? Okay. Alright. So let's make that 1. Nope, not negative 1. Just 1. Alright, so you good with that? Everybody understand? We're good? Okay. So is this is as we've predicted so far, right? Vertical stretch, horizontal stretch. Okay, let's take a look at this h value. So if I light this one up here, oops, darn, I gave it away already. That should be a 0 to start with, right? If we're adding or subtracting here a 0, it's the same as 2 to the power of x. So as h increases, what happens? Now this is a bit misleading as well. It's not being folded down. It is, yeah, let's just zoom out here and watch this again. So I'm going, look at, you see how it's holding the same shape overall. It's just being stretched out, you see? And if we're at h equals 10, here, this corresponding point is exactly 10 units to the right, see that? That's going to show up as 2 to the power of x minus 10. If I bring it back down, look at it, just slides right over. Slides over, there's 0. And now it's sliding over to the left. So horizontal translation, absolutely. Got it? Okay. Very good. Now, finally, k. Y equals 2 to the power of x. So what's it going to do? Up and down. Yeah, I think so. Let's just see what happens here. There we go. Look at that. The whole thing rises. Da-da-da. Ascending to heaven. Okay, wonderful. So if k is 10, look at this. The asymptote here, the horizontal asymptote from 0 becomes 10. If k is 10 and everything else is, we've got a is 1, b is 1, h is 0, and k is 10, that affects the range of the function, right? Now the range is greater, y is greater than 10. Right, so we play that and it just goes, that's the wrong one, play that, and it goes up and down. Alright, now, what I should do I have this down here somewhere? No, oh, there's logs for next day. Okay, so I'm gonna make a new one that has all of the parameters, and then we'll see how they all interact with each other. Okay, so I had to use different letters so I could get sliders here. So D is like our A, F is our B, G is our H, I is our K. All right. So I'm going to deselect this one. We'll have which other one's on? 2 to the X. Oh, I've got this. Okay, but some of them are at 1. Okay, so D is 1. That's fine. F is 1. That's fine. G should be. No. This should be 0. And this should be 0. Okay? Right? Oh, the other one's 2. Oh, yeah. Oh, I know. It didn't do E as a variable. Do you know why it didn't do E as a variable? Because it's a very common base. And in calculus, we use E as a base a lot. So let's just make it something really weird like P. Thank you. Give me a slider for P. So P is going to be, I guess we could have done just 2, right? Let's compare it to 2. Add a slider. Okay. I guess there's a little lesson on how not to use decimals. Okay. So P, I'm just going to make P equal to 2. Okay? There we go. They're the same. See that? Yes? Everybody understand that? Okay. So we won't touch P. We'll leave that as 2, but let's go D. Okay? That's going to be stretching. Right? That's stretching up and down. B, ooh, look at that. Going to the negatives. Yes. Okay, what about F now? Oh, look at that. That's a little bit of stretching going on there. Oh, cool. Okay, G, let's add some horizontal translations. Ooh, funky. Wow, that's great. And what about I? Let's move it up and down a little bit there too. Right on. It's like some kind of like weird dance move or something. Look at that. That is chaotic in a sort of predictable kind of way. Love it. Look at that. Should we slow things down? Okay. So see how they're interacting with each other? Neat, hey? Up, down, left, right, squished in, expanded out. Vertical and horizontal. Wow, that's great. Awesome. Could never do that twice in a row. Cannot get that twice in a row. Okay, so let's stop, and stop. All right. So this graph of green is y equals 6.65 times 2 to the power of negative 1.1 bracket x minus 3.26 plus negative 7.47. So that's what that graph looks like. So as we review in your textbook, A is a vertical stretch. When A is greater than 1, right, it goes up. When A is less than 1, it squishes down. When A is negative, it flips. B. When B is greater than 1, it's a horizontal compression. See that? Y equals 2 to the power of 3x. So when B is larger, it squishes in. When it's between 0 and 1, it extends out. It spreads it out. And when B is negative, it's a reflection in the y-axis. For K, it's a straight vertical translation. Oh, why did they do K? Where's H? Okay, they did K next. So K is vertical, up or down. And H is horizontal translation. Remember, there's no stretches in H or K. When you're graphing this stuff, if you have to graph something, you always do the stretches first, right? Do the stretches first. Change the original graph involving the first stretch. You can do A, then do B, then move that mangled graph there. Move that left or right and up or down. So don't ever start with the translations when you're graphing. Got it? Understand? Any questions? See? Transformations to sketch. Okay. Yay? Nay? Alright. In that case, there's a lot of examples, but we've got a short class today, so it's going to be a little short lesson. And here's the key ideas. I'll let you take a look at those for half a minute, and we'll get your assignment together.